So today I'll be presenting on recent developments in dual function radar and communication systems. And this will actually be presented at the 2023 ISRS Radar Conference. So to begin, as everyone here is familiar with, spectral efficiency is becoming a growing concern for our systems as the amount of available RF spectrum we have is decreasing as bandwidth is becoming a more desirable thing. So one approach to solve the spectral efficiency issue is with dual function radar communication system, where a single RF transmitter would perform both radar and communication service on the same bandwidth. And this is something that's already been done, and we are extending that this DRFC concept to a network of multiple systems that would work simultaneously with overlapping spectral content, which would provide an even more efficient use of limited RF spectrum. So the way we propose to do this is to use a type of modulation that would be amenable to radar service. So in this case, that would be FM continuous wave, and that's non-repeating. These two characteristics would greatly enhance the radar performance and also make sure that the communication stuff that is embedded on the radar would not degrade the radar performance in any way. So to do this, we leverage a spread spectrum, multiple access technique, and continuous phase modulation. So previous work with a spread spectrum, CPM, for comm systems is not suitable for radar, as the repeating codes do not give us enough of a processing gain when we integrate all that up for radar. So we propose using random phase codes that would allow to give us that processing gain so we can take weak targets out for radar. For our specific modulation case, we will be using what's known as STOGI, or the stochastic waveform generation framework, to produce our DFRC transmission. So STOGI produces constant amplitude, so frequency modulated waveforms based off a desired power spectrum template, which will give us good spectral containment, which is necessary for radar. Kind of get to dig more specifically into CPM itself. CPM is a type of frequency modulation where you take a baseband data stream and you're able to map it into this FM signal, which, as it's continuous and phased, provides good spectral containment. And you can see here in the equation that we have our input data vector, which is beta, a frequency shaping filter, which dictates spectral response to the CPM, and the constant phase is enforced via the integration of the phase function. So as I stated previously, the spectral response of this is dictated by this VFT filter, of which for our system would use a STOGI designed frequency shaping filter, which of course is designed off that desired spectral response parameter. So to address how STOGI is different exactly from traditional CPM found in comm systems is, like I said, we're designing it specifically for spectral containment, which is very important for radar. And also to address the multi-user aspect of it, we are multiplying each symbol by a chip or a part of a unique code assigned to each user. And an added benefit of this is it spreads out the symbol information frequency. Since we are only designing for spectral containment, the STOGI filter will not always integrate to 1/2, which means the phase of each symbol is dependent on the phase of the last symbol and will usually be random. And also all of the STOGI filters we are implemented will have a partial response parameter greater than 1. And just kind of a mathematical clarification thing for the Stogie implementation. The modulation index parameter is assumed into the frequency shaping filter. So this is the same thing expressed graphically this time, where you can see there's two traditional frequency shaping filters used for COM CPM. And in this case, we have a rectangular and a raised cosine filter. And then in blue, we have an example of a Stogie filter, which, since we are trying to mask perspective containment, you can see it doesn't look anything like the other filters. And as I said, a consequence of this is it will not integrate to 1/2, and that will become important when we talk about the communications conversion. So just as a mathematical representation of the Stogie signal, you can see we have a similar structure to the COM CPM. In this case, we maintain our beta vector, which is our baseband symbol. But now we add our alpha values, which are the spreading code, which provides the multiple user characteristic of this. And you could also see that the modulation index is now gone. And it is important to note that the signal will still be random even after multiplying with the spreading code, as the product of that is still a uniform binary distribution. With this random spreading code, you're able to achieve non-repeating waveforms. However, that requires that both the radar and the communication systems know what that spreading code is. For the radar, that's simple because the radar is transmitting the signal and looking for that same signal. So it will know that no matter what. The comm system has to have that programmed into it too, but we're expecting that since these systems are designed together, that it will also be able to know that. And then each individual comms user will be able to demodulate their specific signal based off of the alpha code they know. So the receiver for both radar and comms is correlation based, as you can see here in this equation. And like I said previously, everyone must know that we're assuming that each system knows the appropriate spreading sequence, which would just be programmed in. So for our actual communication system receiver, we are using a hypothesis test where we correlate each of the received signal with if 1 was sent, or is in this case a -1 representing a 0 was sent, and just integrating that energy up and seeing which is higher. And although this is a suboptimal receiver for a CPM-based decoder, and the reason we are doing this is because the Stogie filter does not integrate to 1/2, meaning that trying to implement it by Kirby would be a lot more difficult and probably very infeasible here. So this works very well, and especially since our partial response parameter is greater than 1, this also helps deal with some of the ISI imparted by the Stogie filter. So as you can see, the comms receiver performance, when we correlate the received signal with the proper bit that was sent, you get that nice spike there. And then when you correlate it with the opposite bit, you can see that does not show up. So the autocorrelation is much better than the cross correlation, which shows the receiver will show pretty good performance. And this is just a mathematical description of this hypothesis test, where we're just seeing, has the energy shown up more is with a 1 cent or was it 0? So this is kind of graphically showing how much better Stogie performs in spectrally containing versus MSK, where you can see the blue waveform there is the Stogie waveform, and you can see that very nice roll off due to the shaping filter we're applying versus Stogie or MSK, which has much more side lobes and a much more gradual roll off there, which is not good for radar because that generates side lobes in your image and will mask weak targets. And you can see also that Stogie and MSK perform about the same, where Stogie, you're not losing anything to radar, and in fact, you actually get a slightly better noise floor compared to MSK. And the one thing Stogie will impart are these shoulder lobes on the main lobe, and it's a little bit wider than the MSK sense, but as we're not getting that gradual spectral roll off in MSK, Stogie is still the better waveform for still preserving the comms aspect of the system. And this is just showing what a point target looks like using Stogie and MSK. And you can see, even though those shoulder waveforms do show up, you get a better noise floor, and you still get better roll off in the compact response in Doppler. So comparing now the communications, the multi-user communications part of the system. So as you can see, for various numbers of chips per symbol, so effectively time bandwidth product for the data, and also number of users, you can see the bit error rate plots here. So as expected, as the number of users increases, the bit error rate increases as well. And this is just because there's effectively more interference where each user is interfering with each other. So that's expected. And as you decrease the number of chips per symbol, the bit error rate also increases because you have a shorter integration time for the receiver. And in the MSK case, since we're not assuming any noise or multipass because we just want to see the performance of these waveforms, you can see it does have, for each case, does have better bit error rate performance compared to Stogie. But that, of course, comes at a loss of radar signal processing, which is the main goal here. So in conclusion, we have proposed a DFRC mode that allows for both radar and communication service on the same transmitter, while allowing multiple transmitters to operate in the same spectrum. And we have shown that the Stogie approach that we use does not impact the radar performance, which is the main goal of this system here. So even though we do lose a little bit to comms, we're still able to combine these two systems together and provide both reliable comms and radar. Future work we'd like to propose is potentially trying to do a Viterbi decoding with the communications, and also building this into a physically realizable system beyond the simulation.